In section 3.4, we're going to look at the chain rule, which is one of the most important rules in all of calculus. With the chain rule, we will now be able to differentiate a composition of functions. So in many ways, you can think of the chain rule as being the derivative rule that applies to the operation of composition. Let's suppose that we have y, which is equal to f of u, where f is differentiable, and u is equal to g of x, which is a differential function of x. Then, in essence, what we have is y is equal to the composition of f composed with g of x. And this will also be a differentiable function. And the derivative rule for it is as follows. We'll first write it in Leibniz notation. The chain rule says we take the derivative of y with respect to x. We do dy du. And we would then multiply that by du dx. Equivalently, kind of showing it in the function notation, what the chain rule kind of tells us to do is the following. If you look at f composed with g of x, so the most important thing, first of all, is to be able to recognize it as the composition of an inside function with an outside function. So the outermost function is f, the innermost function is g. The chain rule says we do the derivative of the outer function first. So you do f prime composed with g of x. So you leave the inside function alone for the moment. It's going to be f prime composed with g of x. And then we multiply this by the derivative of the inner function. That's going to be g prime of x. So again, in words, to differentiate a composition of functions, we do the derivative of the outside function composed with the inside function times the derivative of the inside function. Let's take a look at example 1. And I'm going to save part A for later. I don't think it's the best illustration of this. But let me introduce this with the notation we just saw a moment ago. So when you look at the function y equals the sine of 2x, we can think of this as f composed with g of x, where f of x is the outer function, that's the sine of function, and g of x, which is the inner function, is equal to 2x. Again, algebraically, we should be able to check this, but if you do f composed with g of x, then everywhere you have an x for f is the function that's the sine of the input, we would just be putting 2x. So according to the chain rule, if we want to take the derivative of this would be equal to f prime composed with g of x times g prime of x. Well, let's come over here. Let's do f prime. F prime of x is equal to derivative of sine is cosine. Do g prime, derivative of g prime, derivative of 2x is going to be 2. So our derivative in this case, so the derivative of the sine of 2x, again, it should be f prime composed with g of x. F prime is the cosine function, so this is going to be the cosine function of 2x, and then we're going to multiply this by g prime. G prime is equal to 2. So there you have it. There's our derivative, 2 cosine of 2x. And as I'm writing it this time, I'm trying to show you how it would kind of fit notationally. We have the f, g. F is the outer function, g is the inner function. As we get more comfortable with this chain rule, I'm just going to start to kind of go through it step by step. So the key is to recognize it as a composition again. So let me show it one more time, just kind of going through the process here. So we see that we have an inner function of 2x, and the outer function is sine. So usually I wouldn't show all of this work. I would simply start off by saying, okay, I'm going to do the derivative of the outer piece. The derivative of sine is cosine. You leave the inside function alone, so it's still composed with 2x. And then from the chain rule, now is when we multiply by the derivative of the inside. Okay. So we're going to multiply by the derivative of 2x, which is going to be 2, and that's where our derivative is coming from. It's 2 cosine of 2x. Let's do another one of these. In example C, we have y equals the square root of 3x squared minus x plus 1 half. We know that typically, and it will still be the case, whenever we want to do a derivative that involves a square root function, we would like to rewrite it as the 1 half power. This time, we're thinking of the inner function as being the polynomial. So if you look at what's on the inside function is 3x squared minus x plus 1, and the outer function looks like something to a 1 half power. We're going to take the chain rule of this. So we begin by doing the derivative of the outermost function. To differentiate something to the 1 half power, we know we bring the 1 half down. We need to reduce the power by 1. 1 half minus 1 is negative 1 half. And for the moment, we leave the inside function alone. So this is still composed with the inner function. And now from the chain rule, we need to multiply by the derivative of the inner function. The derivative of 3x squared minus x plus 1, that should be 6x minus 1. From here, we definitely want to simplify it a little bit. We don't want to leave it with that negative 1 half power. So we have a 6x minus 1. We can put that in the numerator. The 1 half, I can think of it as a 2 coefficient in the denominator. And then we're going to reciprocate this, 3x squared minus x plus 1. And then that will now be to the 1 half power. So there's our derivative. Y prime equals 6x minus 1 divided by 2 times parentheses 3x squared minus x plus 1 to the 1 half power. We'll take a look at part D. First of all, notationally, I think it's a little bit easier to see the composition if we go back and rewrite what this really means. So instead of using the shorthand notation for this power, when we say tangent squared of x, that really means the tangent function of x, whole thing to the second power. And when we write it like this, it's a lot easier to see the composition. The outer function is the squaring function. The inner function is the tangent function. So let's apply the chain rule. The chain rule says we're going to do the derivative of the outer function. To differentiate something to the second power, we bring the power down, reduce it by 1. And now we're going to leave the inside function alone. So it's still going to be tangent of x. And then from the chain rule, we multiply by the derivative of tangent. And we recall that the derivative of tangent is secant squared x. So the derivative for this problem is 2 tangent x secant squared x. We'll come back now, we'll do example 1, part A. I feel like this might be the worst one to start with, simply because it's not always so easy to see A as necessarily a composition, but it really is. You could think of it as the composition of 1 over x with x plus 1. Or if we rewrite it, we can think of this as x plus 1 to the negative 1 power. And now with it rewritten like this, it's kind of easier to see that, okay, the outer function is the negative 1 power, and the inside part is the polynomial x plus 1. We can go ahead and take our derivative. We're going to bring the power down. So we're doing the derivative of the outer function. Bring the power down, reduce the power by 1, leave the inside function alone, and then multiply this by the derivative of the inside function. Derivative of the inside function is 1. And so we get y prime equals negative 1 divided by x plus 1 squared. Another reason why A is probably a horrible example of using the chain rule, although it's nice to see it, that it actually works, is that we very easily could have done the quotient rule for part A and would have given us exactly the same answer. But the one thing that will be kind of illustrated in part A is that it shows that we actually can almost avoid the quotient rule entirely if we choose to, because any denominator could always be rewritten as that factor to the -1 power, and then in essence that avoids the use of the quotient rule, and it would turn into a chain rule derivative. So at least it kind of gives us some opportunity, and in some situations that might even be preferable, depending upon what the quotient rule might look like. But this is our chain rule. Very, very important rule. We definitely want to make sure that not only do we learn it in this section, but you really want to master it, because it's going to be important throughout the rest of the class. And just to kind of summarize, what does the chain rule say? The chain rule tells us how to differentiate a composition of functions. You do the derivative of the outer function, compose with the inner function, so the inner function is initially left alone, and then you multiply that by the derivative of the inner function. So in this case, we're calling that g prime of x. Let's take a look at example 2. We're asked to find the derivative dy dx for y equals x squared plus 1 to the third power. We look at it, we say, okay, again, this is a composition. The outer function is x cubed, or the cubic function. The inner function g of x would be x squared plus 1. So because it's a composition, we need to use the chain rule to find that derivative. We start by doing the derivative of the outer function. The derivative of something to the third power would be bring the 3 out, reduce the power by 1, leave the inside function alone, and then from the chain rule, we're going to multiply by the derivative of the inside. The derivative of x squared plus 1, that's going to be 2x. So for us, dy dx is equal to 6x times x squared plus 1 squared. We can use the chain rule to create a more general form of the power rule. So if you recall earlier, we've already looked at the derivative of x to the n. So if y was equal to x to the n, we now know that y prime is equal to n x to the n minus 1. You just bring the power down and reduce the power by 1. If we generalize it, let's suppose that instead of having just simply x to the n, let's suppose that y is equal to u of x raised to the n, where the inside part is a differentiable function of x. Well, if that's the case, then this is a composition. It's the composition of the nth power function with the function u. And then according to the chain rule, we would bring the power down, reduce the power by 1. So we're going to get n to the n minus first power, leave the inside part alone, so leave the u of x alone. And then from the chain rule, we need to multiply by the derivative of the inside function. The derivative of u with respect to x, we would call that du dx. That's with the Leibniz notation. If you wanted to write this in the prime notation, then it would simply be n u to the n minus 1 u prime. And if you look in the appendix of the book, or if you have the physical cover of the book, oftentimes the theorems that are stated at the front of the book will be kind of in the more general form that uses the chain rule. As another example of this might be a little bit of an aside, but you probably wouldn't see the simple rule derivative of sine x equals the cosine of x in the front of the book. What they will typically do is state the more general form, allowing for the possibility of there to be more than just a function of x on the inside. More often they'll state it more generally as d dx of sine of u, which would still be the cosine function, but then from the chain rule, we would multiply by the derivative of the inside function. And if u is a function of x, then its derivative we would call u prime. So not only can we generalize our power rule, we're actually able to generalize any of the basic derivative rules that we've learned up to this point. Let's take a look at example 3. Again, they want us to find the derivative f of x equals 3x minus 2x squared whole thing cubed. We recognize this again as a composition. It's the third power with the polynomial 3x minus 2x squared, so it's a composition. We're going to do the derivative of the outer part first. Going to bring the power down, reduce the power by 1, leave the inside function alone, so that still stays the same. And now from the chain rule, we need to multiply by the derivative of that inside function. the derivative of 3x minus 2x squared is going to be 3 minus 4x. So f prime of x is equal to, I'll just leave it in factored form. There's no need to have to multiply this thing out, and actually it's preferred that we don't. So there's our derivative on this one. F prime of x equals 3 times 3 minus 4x times 3x minus 2x squared, quantity squared. Let's take a look at example 4. This is a very important kind of question, and one that's kind of leading a little bit. In example 4, we're asked to find the derivative, so we want to find f prime of x, but in addition to that, we want to find any places or any values of x for which the derivative would be equal to 0, and also any for which f prime of x may not exist. Okay. So first things first, in order to analyze the derivative, we need to get it. So here our function, it's the cube root of x squared minus 1 quantity squared. We can rewrite this. This is a combination of a radical and a power. So we can write it with a rational exponent. The cube root of something squared is the same thing as the 2/3 power of that quantity. So f of x is really equal to x squared minus 1 to the 2/3. And so this is the composition of a 2/3 power function with the polynomial x squared minus 1. We can go ahead and take the derivative. F prime of x is equal to, we're going to bring the power down, reduce the power by 1. 2/3 minus 1 is negative 1/3. Leave the inside function alone. And again, we need to do the chain rule. So now we need to multiply by the derivative of the inside function, which would be 2x. We want to simplify this. We can write it as a 4x in the numerator, the 2 times the 2x. We have a 3 in the denominator, and then we can write it as x squared minus 1 to the 1/3 power. So for this particular problem, this is called our derivative. The next thing we're looking for is they ask us to find any places where the derivative would be equal to 0. Well, that would occur when 4x divided by 3x squared minus 1 to the 1/3 power equals to 0. And to solve this fractional equation, what we would do is the common algebraic trick, multiply both sides by the denominator in order to clear off these fractions. I'm just going to squeeze it and wedge it in here, times 3x squared minus 1 to the 2/3. It'll simply reduce to 4x equals to 0, divide both sides by 4, and so we get x equals to 0. So this is a place where the derivative would be equal to 0. Coincidentally, if we look at the graph of this function, it would be the place where you would have a horizontal tangent line. Because remember, if the slope is equal to 0 at the point, then that means that it has a tangent line with a slope of 0, which means that the tangent line is horizontal. We also would like to ask the question, well, where is f prime undefined? So where is f prime undefined? Well, f prime is represented by a fraction, and we know that anywhere the denominator is equal to 0, that operation will be undefined. So let's solve this for x. Divide by 3, divide by 3. These cancel. We get x squared minus 1 to the 1/3 equals to 0. To get rid of a 1/3 power, if you want to, you can go back to thinking of it as a cube root. The opposite of a cube root would be to cube at both sides. We get x squared minus 1 equals to 0. You can take the 1 to the other side, then use the square root property. X equals plus or minus the square root of 1. which should mean x equals plus or minus 1. So we have two values of x in which the derivative is undefined. They are x equals plus and minus 1. And when I upload this video to YouTube, I'll actually show you the graph of this thing. What you would see is that this graph will have cusps at plus and minus 1, which are kind of like those short, sharp corner-looking things. And so those will be places where this derivative would be undefined, and that's precisely what we found when we did the analysis. Let's take a look at example 5. We're asked to differentiate the function g of t equals negative 7 divided by 2t minus 3 squared. So just looking at the way this function is set up as is, we could certainly go ahead and begin by applying the quotient rule, but we can avoid the quotient rule entirely if we simply take a step of rewriting this. I can bring this denominator term into the numerator if I rewrite it with a negative exponent. And now what we have is a constant multiple times some function. So we can take the derivative of it. G prime of t would say leave the constant multiple negative 7 alone, and then multiply it by the derivative of this piece. Well, this piece is yet another composition, and to do the derivative of a composition, we need to use the chain rule. I'm going to bring the negative power down. I'm going to reduce the power by 1. Negative 2 minus 1 is negative 3. Chain rule says leave that inside function alone, but then on the outside, we're going to multiply by the derivative of the inside function. The derivative of 2t minus 3 would be 2. And now all we want to do is just kind of rewrite it by simplifying. Negative 7 times negative 2 times positive 2 should give us a positive 28. And we're going to have a 2t minus 3 cubed in the denominator. So it's a good exercise if you want to. Try to redo the derivative in example 5 by using the quotient rule and see which of the methods is actually easier. It turns out, at least in my opinion, that by doing this rewriting it step, it becomes a pretty run-of-the-mill chain rule problem, which makes the computation not so bad. And in my opinion, a little bit easier than doing the quotient rule, because the quotient rule for this one would require a lot of simplification to get down to this final answer.